This part is referring to analyzing impact of jets. We're not talking about the jets that fly in the air. Of course, it's the same thing because the jet that is coming out with the liquid may behave in the same way. This time we're talking about water or a liquid coming out of some hose at a speed. That is the jet we're talking about. Now, in this scenario, imagine a jet coming out from a hose or from a pipe. It's directed towards a plate or a wall. Now, there are two things that may happen. If you direct the jet towards a plate, for example, the plate may start moving or it may remain stationed. Whatever happens after that, we are able to calculate the force that will cause that. We can even go ahead and calculate how efficient the jet is. So that is what this analysis is all about. We'll take our time to analyze how those jets behave. So once again, here we are referring to Newton's second law of motion, which is again, it applies to same F is equal to ma, and then we'll try to rearrange it and apply it to a jet of water. So here we start with a case where when that water comes out, it hits a stationary plate. When that happens, the first thing we can notice is that we have the rate at which the water is coming out or the liquid is coming out of the pipe, which is the product of area and velocity. Then also the mass per unit time. How do you find it? We are going to multiply, like we always say, that mass is density times volume, because this is volume per second. So density times that product, which is area times velocity, gives us mass per kg, or rather mass per second, kgs per second, mass per unit time. So density by area by velocity. Now, here we're talking about if we go back to a case where the plate, the final plate where the liquid is falling remains stationed, then one of the velocities, meaning the final velocity, is 0. That's why you may see some negative as you do the calculation. So what happens to the force exerted on the plate? We told this is equal to the rate of change in momentum. That is meaning mass per second times change in velocity. Mass per second times change in velocity. There we have it. So meaning mass per second, which is density times area times velocity, times that change in velocity. So mass per second, kgs per second times this. It is giving us the force. We are representing the force, denoting the force by letter P. So P is equal to density times area times velocity. And then we introduce that change in velocity also. Now, these are basically the same as V times V, so you have V squared. Now, suppose the plate is inclined at angle theta, or perhaps as the jet is striking the plate, that jet is striking the plate at an angle. That's what we're referring to here. Then if that is the case, we'll just say we introduce cos theta. So P being the force equal to density area times velocity squared cos theta. Then you've resolved. Here we just need the force in one direction because it may be forced to move or it may be forced to remain stationed because of the reaction from there. Let's start with a case where the jet is at 90 degrees to the plate. The water coming from the hose or the liquid coming from the hose hits the plate at 90 degrees. So in this case, the scenario is simple because you have final minus initial squared. That's it. And then we'll just go ahead and leave it like that. These are the two velocities. And what if it's inclined? If it's inclined, we use this formula, density area, then V cos theta minus U, everything in the brackets squared, divided by cos theta, where theta is the angle of inclination. That is the angle of inclination. Okay, now one thing you'll notice is that these are the formulas we'll be using, either the one on top where it's at 90 degrees, or this one where it is at an angle specified. So here's our example. The first example, we told the jet of water comes out of a 20 millimeter diameter nozzle with a velocity of 10 meters per second, hitting against a stationary plate, meaning that the plate did not move. The final velocity is out. Determine the force exerted by the water on the plate. So the information given, first is the diameter of the jet, which is area, pi times 0.02 squared over 4. We get our 3.142 by 10 power negative 4. Velocity, we thought the velocity is 10 meters per second. Density, 1000 kg per cubic meter. That's all. This density, the 1000 kg per cubic meter, is because this is water. The density of pure water is 1000 kg per cubic meter, so you do not have to start searching for it unless that water is contaminated and another value has been given. So here, we're not even going to stress because the other velocity is cancelled out. You just remain with this one. Density area times velocity squared. So density times the area times the square of the velocity. Then our answer is 31.42 newtons. Now, our scenario now here is, what if this is at an angle? Here is the same jet, but diameter 20 millimeters, and then it is striking a plate at 30 degrees. And then the plate is already moving at 1 meter per second. But then the jet is coming out at 5 meters per second. Here, the secret is you don't need to rush. What you need to do is to, first of all, need the force, the work done, and the efficiency. What information do we have? The area, pi d squared over 4 is the same formula we're using. So pi times 0.02 squared, then divide by 4. You get 3.142 by 10 raised to the negative 4. Velocity v, this is the velocity of the jet. It's 5 meters per second. Initially, the plate is moving at 1 meters per second. So that's our u. Then angle at which this is striking the plate, or the angle of inclination of the plate, 30 degrees. 30 degrees. So this is the information we have. And what do we need to do? Let's get the force first of all. Density, this is still water, 1000 kg per cubic meter. If it's not water, you'll be given the properties of that liquid and calculate the density according to the parameter provided. If it's relative density, you multiply by 1000 and you get the actual density. If it's specific gravity, you do the same. But if it's specific weight, you divide by G and you are there. Whichever the case, it's not always going to be water coming out of a jet. It can be any other liquid. And whatever density of liquid you've been provided is the one you use here. In this case, what we have is water. That's why we are using 1000 kg per cubic meter. So our force is in density times area. Then we have v cos theta minus u, everything in the brackets, squared over cos theta. So P is equal to, density is 1000 times 3.142 times 10 to the negative 4. Then 5 cos 30 minus 1. Here we are saying that the V is 5, angle is 30, U is 1. Then the angle there is 30, so it's still cos 30. Once you do that, our answer is 4.023 newtons. The work done is force times, work done per second is like power. So this is supposed to be force times velocity. So if I want, I can even say FV. So P is representing the force, so that's why we're saying P, which is the force multiplied by the velocity. This product gives me the work done per second. So the velocity is 1. And remember the work being done, it's the work done on the plate. So 4.023 times the velocity at which the plate is moving, which is 1 meters per second. So 4.023 times 1. Work done therefore becomes 4.023 joules per second. What about the efficiency? Efficiency compares the work output over the work input. So in this case, we'll say net energy of the jet, that's the work input, because that's the one which is causing the plate to move. So half mv squared. Our mass is density times area times velocity. So if you follow that equation, v times v gives us v cubed. So you can substitute half times density times the area times the velocity raised to power 3. Kinetic energy of the jet, therefore, is 19.6375. That is our input. Then what is the output? The output is what we just found as the work done on the jet. So the work done per second, then energy of the jet per second. Energy of the jet per second, 19. Work done per second, that's the one we just found as 4.023. 4.023 divided by 19.6375 times 100, then my percentage is 20.5%. That's how efficient this jet is. So with that, you can take time again to go through these 5 questions with answers already provided.